Hello everyone. In this video, we will solve a problem in topology from exercise 2.5 P10 of Munkres.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Given is a set A and indexed family of spaces, and also functions, indexed family of functions from the set A to the corresponding index space X alpha. We are supposed to show that there is a unique courses topology T on A, relative to which all the functions f alpha is continuous. That means we are supposed to find a topology T which is coarsest to possible topology on A, which means if you take any other possible topology on A, that will be a say T prime, that will be a superset of T, or T is a subset of that any other topology T prime on A, any other possible topology. So we need to find such a topology T on A, and we need to prove that that is unique. So before going into this question, let us first learn what is a subbasis and a few properties of functions. It is very simple. We all know what is a topology on a set, right? It is a collection of subsets of a space whose finite intersection are also present in that, and arbitrary union are also present in that. That is topology. And subbases of this topology mean, let us say S is a subbasis of a topology on the set A, is a subbasis of the topology T on the set A. Then it means that finite intersections of elements of S forms the basis of the topology T. Finite intersections of elements of S forms basis for the topology T. Then we say that S is the subbasis of the topology. The elements of the subbasis are nothing but open sets of A. Basically, they are some subsets of A, to be precise. So this is called subbasis. And second thing is that if you have a function from a domain to a codomain, suppose, and this function has a set, and let us call that to be set u1, and it also has a subset u2, and let's say the function that takes you from domain to codomain is f, then f inverse of u1 is a subset of domain, and f inverse of u2 again is a subset of domain. Notice here that then what is f inverse of u1 intersection u2? It is nothing but f inverse of u1 intersection f inverse of u2. Why this is true? Suppose an element x belong to u1 intersection u2. Then it belongs to f inverse u1 by definition, and it also belongs to f inverse of u2. So f inverse of x belong to f inverse of u1 by definition, and also to F inverse of U2, and hence it belong to the intersection of two sets. Now suppose say that some element Y belong to, let us consider an element T that belong to both F inverse of U1 and F inverse of U2. Then it must belong to U1 and U2, because F of T must be present in U1 by definition, and F of T must be present in U2 as well. So basically, any element in this set is a element in the set, and any element in my LHS is my element in my RHS. So both sets are actually equal. So these, with these two being learned, let us directly jump into the question. So for part A, I will define the subbases. First, we want each and every function to be, each and every function f alpha from A to the space x alpha to be continuous. Consider the basis of the space x alpha to be curly B alpha. That is the basis, which means it is a again collection of subsets of the space x alpha, which forms a basis of the topology on x alpha. Then I will consider f inverse, f alpha inverse of B alpha. We know that B alpha is a collection of subsets of x alpha, and each subset is taken an inverse image. So this is a collection of subsets of A, right? Because f alpha inverse is a function mapping to the domain of A. So they are collection of subsets of A. And this is defined for each alpha, for each index alpha in J. I define this set. Say this is curly C alpha. Now, the union of all the C alphas for alpha in J forms a subbasis for the topology T on A. First, why is this a valid topology? Why is this subbasis which is used to form the topology T a valid subbasis? In order to prove the validity, we first have to note that the functions f alpha must be continuous upon this topology on A. Now, to prove that each f alpha is continuous, you will have to consider the condition for which a function will become continuous. That is, any inverse image of basis elements of my codomain must be open in domain. That is the definition of continuous function. We can also say any inverse image of open set is open in the domain, but it is also equivalent to saying that any inverse image of basis elements is open in the set A. Consider a basis element. First, let's consider the function f alpha 3, suppose some alpha 3. So that goes from x A to x alpha 3. And let us consider the basis element B2, which is a subset of x alpha 3, and it is a element of the basis of alpha 3, basis of x alpha 3. Now we know that f alpha 3 inverse of B2 is an element of C alpha. C alpha 3 by definition of C alpha as given here. And that means it is an element of subbasis, right? And we know that finite intersection forms the basis, and F inverse F alpha 3 inverse of B2 is by itself an element of subbasis, which means it is an element of basis, because taking that thing as a one element of basis will give us, because finite intersection means it can be one element or two element or three element or so on. So F alpha 3 inverse of B2 is an element of basis, which means it is open in A, and that means F alpha 3 is a continuous function. Similarly, this is an arbitrary index alpha. So basically, it is continuous for all index alpha. Now, we have proved that it is a valid topology for which the function f alphas are continuous. All function f alpha. But how will I prove that it is the coarsest topology? For that, you can think that any topology that you put onto the set A for which the functions are continuous must have f inverse of its basis element to be open. F inverse of, let's say that we consider alpha 3 again. F inverse of alpha 3, F alpha 3 inverse of B2 must be open in A for any topology on A. This is not only for B2, the element B2, it is for any basis element of X alpha 3. And similarly, not only for X alpha 3, if you take any space, let's say X alpha 7, alpha 8, all its basis element inverse must be open in A, which means its finite intersections are open in A. And that means the any topology that you put on A must contain the basis elements of our topology that we defined earlier. That is this, let's call this topology to be curly T or tau. The basis of tau, all the basis elements of tau must be open in any topology on A, because basis elements are nothing but finite intersection of F inverse of basis in X alpha. So that must be open in any topology, which means if you take any basis element of the topology tau, any basis element, then that is already open in any topology that you choose on A, which means it is the coarsest possible topology, because we know that any open set in U, any open set in tau must be arbitrary union of basis element, which is already which in which each basis element is already union of some open sets in any topology. That means tau is the coarsest possible topology. Now let us come to part B. So we will have to prove that this S beta, which is the collection of all F inverse of open sets in X beta, forms, and that taken union for all indices forms a subbasis for the topology T. It is very easy because now that we have defined the topology tau, if you take the subbasis S to be union of S beta for beta in J, and S beta is defined as a f beta inverse of u beta, such that u beta is open in x beta. This forms a subbasis of the topology T, is what we have to prove, which means its finite intersection forms the basis of topology tau, is what we have to prove. Now that we have known what are the basis elements of the topology tau, let us try to do this. Suppose if you have finite intersection in the sense beta 1 inverse of u beta 1 intersection f beta 2 inverse of u beta 2 intersection till f beta, let us say for example some f beta 71 inverse of u beta 71. Then if you consider this basis element, this is a random basis element. We know that this u beta 1 is a union of some arbitrary basis elements of x beta 1, right? So we know that f beta 1 inverse of u beta 1 is nothing but f beta 1 inverse of some union of basis elements of some arbitrary basis elements of x, it is in the space x beta 1. Now this can be written as union f beta 1 inverse of each of the basis element t in the space x beta 1. Now we know that these are basis elements of topology tau, basis of tau. That means their arbitrary union is already open in tau, which means it all these are open in tau. Suppose let us consider an element y of this basis element of, let's say this topology is t prime. So this is a basis of t prime, and let's consider a element y. Now by definition of y, there is a basis element in x beta 1, say b beta 1, whose f beta 1 inverse is a subset of f beta 1 inverse of u beta 1, and it contains the element y. This is by definition. So similarly, for all the 71 open sets, you will have the corresponding f beta inverse of the 71 open sets. Now I can clearly say that y belong to f beta 1 inverse of b beta 1 intersection f beta 2 till f beta 71 inverse of b beta 71, which is an element of the, which is a basis element of the topology tau, because it is finite intersection of elements of its subbases. We know that the elements of its subbases are f inverse of the basis of different spaces, and hence we can see that the topology tau is finer than T prime. And we know that T prime is finer than topology tau because topology tau is the coarsest possible topology. So that both imply tau equal to T prime. That is, both topologies are the same. Now let's go to the C subdivision. Show that the map y to a is continuous relative to tau if and only if each map f alpha of G is continuous. So they are asking us to prove that the map y to a, which is represented by G, is continuous relative to tau. Is given the topology tau is continuous if and only if f alpha of G is continuous. So how will I prove this? Very simple. First, let's go one way. Assume that G from y to a is continuous, and let us prove that f alpha of G is continuous. Since G from y to a is continuous, and by definition of the topology tau, we know that f alpha from a to x alpha is continuous for each alpha. Now we know that composition of two continuous functions are always continuous, and hence G, which takes from y to a, then applied on f alpha again, which takes from a to x alpha, is continuous for each alpha. This is very easy because composition of functions are continuous. Let us try to prove the other way around. Assume that the composition of functions is continuous. Then let's prove that G from y to a is continuous. So supposing that this is continuous for each alpha, let's erase this. Then I can say that we know that f alpha of G is a function that takes you from y to x alpha. So this is continuous, which means any open set on x alpha has its let's call this function to be h, will have the h inverse to be open in y, right? That means let us take an alpha, let's say alpha 17, and take this is, let's call it as h alpha. Let us consider h alpha 17. We know that h alpha 17 is continuous, and hence if you consider a basis element b alpha 17, then f alpha 17 inverse of b alpha 17 is open in y by definition of continuity. And similarly, this is not only for this basis and this space. This is true for all bases and all spaces. All spaces x alpha and all bases inside that particular space x alpha is open in y. Now, does it just mean that the function g from y to a is continuous because what are all the basis elements of a in the first place? The basis elements are finite intersections of, let's prove that this is continuous. So let us take the basis element of a. It's called f alpha 1 b alpha 1. It's inverse intersection f alpha 2 b alpha 2 inverse till f alpha, let's take till 30 this time, and b alpha 30, the inverse of this. So this is open. This is a general basis element of the topology tau on A. Now what is its inverse image? As we already know the rule, this inverse image can be rewritten as G inverse F alpha inverse of B alpha 1, where F alpha inverse takes you from set X alpha to A, and G inverse takes you from A to Y. Intersection G inverse of F alpha 2, this is alpha 1 and this is alpha 2, and this happens till alpha 30. G inverse of F alpha 30 inverse of B alpha 30. Now we know that since F alpha of G, F alpha of G is continuous, we know that, and B alpha 1 is open in, and B alpha I is open in xi, x alpha I. That imply by definition of inverse, G inverse of F alpha I inverse of B alpha I is open in Y. And we have finitely many intersection of open sets, and this is then open in Y, and hence you will get that any basis element taken the G inverse will be open in Y, and so G is continuous. This proves it very easy. Going to the last part of this problem, we have the product space pi x alpha. We have f from A to the product space pi x alpha, which is defined to be, which is very easily defined as f of A is nothing but f of f alpha for alpha in J of A, right? Now it is given that Z is the subspace f of A of the product space. Z is nothing but the image of f of A, and we are supposed to prove that f of each element of tau, each element of tau is open in Z. That's what we have to prove. Now we know that any element of tau is nothing but an arbitrary union of the basis elements, where bi belong to the basis of tau. This is by definition an open set of the topology tau. Now this can be written as union, basis arbitrary union for basis element in sorry, this should be curly b tau of f of bi. So what is the basis element bi? We know the basis element of bi will look like finite intersection, let's say from uh, I equal to, or j equal to 1 to 50, 53, suppose, of finite intersections of the inverse of basis elements of x alpha i's. So f alpha j inverse of b alpha j. So here, please remember that this basis b prime is the basis of b prime I is the basis of topology tau, whereas b alphas are basis of x alphas. So now we have to prove that this is open in Z. So if you consider this is nothing but union of f of this becomes let us consider this to be f f of f inverse alpha j. So in that index alpha j, you will have b alpha j cross. This is valid for any alpha j. Let's take, you have in the index alpha 52, suppose, you will have b alpha 52. In the index alpha 3, alpha 53, you will have b alpha 53. And the corresponding values of the remaining indices. This is how the f value looks like, right? Now, why should this be open in Z? So, what is Z? Z is the subspace f of a in the product space. I know that in the product space, b alpha 52 cross b alpha 53, and the remaining just takes the entire x alphas. So, this product where only the alpha 1, alpha 2, alpha 3 till alpha 53 takes the basis element b alpha 1, b alpha 2 till b alpha 52 and b alpha 53, whereas all other thing takes the entire space. That is a basis element in the product space. So we know that this is open in product space, that is pi x alpha. Now if you consider the space f of a of this, if you consider this open, let's say this is u, open set to be u. If you consider this u intersection f of a, which is open in Z, then we could clearly see that these two sets are the same. This one and this one. And hence, this is actually open in Z. Because this is not exactly cross, you will have the indices alpha 52. This is basically some pi x alpha where alpha belongs to J, where X alpha J must belong to B alpha J. That is the only condition that we have. And now the entire thing comes into picture, that these two are actually the same. Because for if you take in B alpha 32, suppose, if you take an element X alpha 32, then you will get X alpha 32 to be your element of the index alpha 32, whereas all other elements will be the corresponding. If you want to suppose consider the alpha 33 index, it will be F alpha 33 of F alpha 32 inverse of X alpha 32. So it will be basically F of, so this is basically F of F alpha 33 inverse of F alpha 32 inverse of X alpha 32. And that's what you get here, which is basically in F of A and in U, right? So like this, you can prove that every element in this is an element in this, and every element in this is an element in this. And so both of them are equal sets, which means it is open in Z, and arbitrary union of open sets will always be open in Z. And hence, F of element of alpha is open in Z. So think about this. We will discuss more problems soon.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.